And then we can have the next look at task 13, which is once again about distance conversion. And here we have, again, a source that has a frequency of 1 megahertz. And at this frequency, it creates some electric field strength with a certain level. And the level is not directly, or the field strength, as said, is not given directly as a field strength, but at this level in decibel, at some distance of 200 meters. And it's postulated that this source is a magnetic source. It's a magnetic dipole. It's some kind of loop antenna. So let's say we have a power electronic circuit. Somewhere a current is going on a loop, maybe on a printed circuit board. The loop is small in comparison with the field strength, so we can assume it to be a magnetic dipole, and then it still creates this electric field. And so question is, how large is the magnetic field strength at the distance of 5 meters? So if we go closer to the source, and now in the next task, it's a current loop with a certain radius, and how large is this current in the loop? This is also what needs to be calculated. So I will, as usual, use blue for subtask A. And yeah, so how can we calculate this, or what formulas do we need to use here? And which conversion do we need to mind first, or what would you calculate in this case? If we look back to the previous task, what have you calculated? What have we calculated at first? Wavelengths. So let's also start with wavelengths here. Wavelengths, lambda is c divided by f. And what was the value of c? 3 times 10 to the power of 8 meter per second. And the frequency here is 1 megahertz. So mega is 10 to the power of 6 and hertz is 1 over second. So now in this case, we get 300 meters. Before we had 100 meters for 3 megahertz. For 1 megahertz, we just have, we get 300 meters. So this is the wavelengths. What does depend on the wavelengths? That what we also probably need for this task? This transition distance. And the transition distance could be calculated by R0. And how could I calculate this? Lambda by 2p. And so if lambda is 300 meters, and if we divide by 2p, if we divide by 6, we get something like 50. And because p is a little larger than 3, we should get something that is slightly less than 50. So let's say here clear all, so that I don't have any old values, and maybe clear the command queue and say our frequency is 1 megahertz. C, I might have the C value there, and I might have the formula to calculate lambda there, and lambda is 300 meters. And I should also have the formula to calculate R0, and it's, as said, slightly smaller than 50. So 47.7 meter. So this distance then is in the far field, but this distance here is in the near field. Okay, so how do we need to do the conversion? We use the same formulas as before. This one for the far field and this one for the near field, but because it's a magnetic source, we need to use an exponent of 2 in this case. So from this far field, we get the transition, the field strength at the transition distance from the far field distance. And then, so it was always multiplied by R1 divided by R0. This should be the proper order. Yeah, and so this is, I will explicitly write the exponent of 1. This is the far field conversion. From the far field to the transition distance, and then from the transition distance into the near field distance, E2 equals E0 divided or multiplied with R0 divided by R2, and here we need to use an exponent of 2. This is the near field thing. Okay, so then some remaining intermediate step that we need to do before we can apply these equations. Yeah, we need to convert this level. So how can we from the level, I mean this is the level of the field strength at position 1, how can we convert this into a field strength? How do we get E1 from this level? So, yeah, so this here was, exactly, so this here on the top, this was 20 times the decadic logarithm of E1 divided by 1 microvolt per meter by the reference value, if this is given in dB microvolts per meter. So now we have this level, we want to have E1. So how do we get E1? So first thing is we need to get rid of this 20. So we take our level, we take this level, let me switch back to blue again. So we take this level LE1 and divide by 20. So now the 20 is gone. Now we need to use the inverse of the decadic logarithm. Yeah, antilog, and antilog is exponent. So, and the base of this logarithm is 10. Decadic logarithm. It's not natural logarithm, it's decadic logarithm. So 10 to the power of this. And so, okay, then we have only this argument here of the logarithm function left. And now we need to get rid of our reference value. And we divide, in this formula, we divide by the reference value. So here we need to multiply with the reference value. Okay, so multiplied with 1 microvolt per meter. Okay, so then I think I can just once again use Octave and do the number crunching and calculation there. So our level, the level of this electric field strength was 46. And yeah, so we can probably also just do some calculation by our head in a second. So E1, if we just apply this formula, should be 10 to the power of this level divided by 20 and then multiplied with the reference quantity, and the reference quantity is 1 microvolts per meter. This is 10 to the power of minus 6. So before I hit enter, so we have here 40 dB and 6 dB. 6 dB for root power quantities like an electric field strength was which factor? If you increase something by 6 dB, how larger does it get? How much larger? Say again?
1 million.
No, yeah, if you have 10 to the power of 6, okay, that's 1 million, but not 6 dB. 6 dB does not mean a power of 6, because we multiply with 20. Yeah, so the decadic logarithm, okay, the decadic logarithm of 1 million is 6, but it's 2. So 6 dB means a factor of 2. 40 dB means a factor of and this is something that you need to have in your mind. So 0 dB means a factor of 1. So 20 dB for this root power quantities like voltage, current, electric field strengths, and so on. So if we have 20 dB, it means the logarithm must be 1. So the logarithm is, the decadic logarithm is 1 if the argument is 10. Okay, so if this should be 40, then the decadic logarithm exactly should be 2, and then we have 100. So 6 means a factor of 2. Yeah, if I write it like this, maybe, okay, 6 means multiplied with 2, and 40 means multiplied with 100. So at the end, it should be 200. So what we get here, what we calculate here should be 200, not exactly, because it's not exactly 2, oops, wrong page, but approximately. Okay, and so as you can see, we get 200 microvolts per meter. If I take this E1, multiply it with 10 to the power of 6, we get 200 microvolts per meter. This is 200 microvolts per meter. And so now we can, of course, take this, insert it here, and then we can take this and insert it over there. So maybe do it like this. So this is what we will insert there, and then we will take this and insert it there. So next step is to calculate E0. And E0 or E0 is E1 multiplied with R1 divided by R0, and this to the power of 2. No, this just to the power of 1 because we are in the far field. And so our E0 should be larger because we go to smaller distances. We go from 200 meters to approximately 50 meters, which is a quarter of the distance. So the field strength should increase by a factor of 4 approximately. And we can check, and it's not yet defined our distance here. So R1 was 200 meters. And so, yeah, so from 200 microvolts per meter, we increase to 800 microvolts per meter approximately. If I take this, multiply to 10 to the power of 6, yeah, we get slightly more than 800 microvolts per meter because we go to something that is smaller than 50 meters.
200?
The R1 is 200.
No, just in the...
I think it's 200.
Okay.
That's 200. Yeah, this should fit. Yeah, and so we had not 50 meter, but something slightly smaller than 50 meter, and that's why we get something slightly larger than this 800 microvolts per meter. Okay, so now we can use the last formula, E2 equals E0 multiplied with R0 divided by R2, and I forgot to set R2, so it will throw an error, but no problem. And we need this to the power of 2 because we are in the near field of this magnetic source. And R2 should be 5 meter. This is given there in the task. And so if we take this and calculate it, now of course it gets larger, it grows larger. Yeah, so we go approximately from 50 meter to 5 meter. So we decrease the distance by a factor of 10. So our field strength should get smaller by a factor of 10 squared. So we increase by 100 approximately. And so we go from 800 microvolts per meter to 8,000 to 80,000 microvolts per meter, and 80,000 microvolts per meter are approximately 80 millivolts per meter. So if I convert the E2 into millivolts per meter, yeah, so we get not 80 but a little less, which also makes sense because we did not start at 50, we started at something else that was already a bit smaller. Okay, so yeah, maybe let's take this and move it a little bit to the side so that I still have some space here to write the results. And yeah, so we got 835.7 microvolts per meter in the far field, and we got 76.2 millivolts per meter in the near field. Okay, subtask A is done. Which questions do you have so far?
It's magnetic field.
And it's not yet done because, very good point, the task asks not for the electric field but for the magnetic field strength. So the next step that we still need is to convert our electric field strength that we have just calculated into the magnetic field strength. So how do we do this conversion from electric field strength into magnetic field strength? With eta, because we said, okay, eta is the ratio between the electric field strength and the magnetic field strength. So if we know eta, we can calculate the magnetic field strength, because it will just be E divided by this eta. So now the question is, how large is eta? If we are in the far field, eta is, how large is it? 377 ohm, approximately. So we can, in this far field, we could just do the conversion and say, let me go to MATLAB. So eta 0, I will call it, is 377. And so H1 is just E1 divided by this eta 0. And so we will get something smaller. And if I convert this into, let's say, microampere per meter, so we get 0.529 microampere per meter. Okay, so now we could take this value and do the conversion into the near field once again, by saying, okay, H2 should be H1 multiplied with R1 divided by R2. And now which exponent do I need to use? 3, because we are in the near field of this magnetic source. So if I use this formula, do this calculation, and say H2 is H1 multiplied with R0 divided by R2, and now to the power of 3, we should get something larger, because we go into the near field. And so we get, once again, let me multiply this with 10 to the power of 6. So we get 460.8 or 0.9 microampere per meter. 460.9. Is this correct? What do you have calculated? Microampere per meter.
The first one is correct.
The first one is correct, and this should probably be also correct. We can do a check. So how could we check this result for the magnetic field strength in the near field? I mean, we had already calculated this electric field in the near field. So we could do the same conversion like here, but now in the near field. And so in the near field, our eta at this position 2, so now we take the formula that we have also already written down for the task before. So eta in the low impedance field in the magnetic near field is eta 0 multiplied with R divided by R0. So eta 0 multiplied with R divided by R0. And if we insert something like our R2 that is smaller than the transition distance, then we get also something that is smaller than our eta 0 in this case. So 377 ohm multiplied with 5 meter divided by the 47.7 meter, and I will do the calculation in Octave and say, okay, eta 2 is eta 0 multiplied with R2 divided by R0. And then we should get something that is smaller than eta 0. And because we go down by a factor of 10, it should be 37 point something. Yeah, and so we get not 37, but 39.5, let's say. 39.5 ohm. And so now if we use this and say, okay, our magnetic field strength at the second distance, we also get from the electric field strength that we calculated before, right? That we calculated here. So we take this and divide by eta 0, what we calculated over here. So also take this and insert this into this formula here. And hopefully if we do this, we should get the very same result as before. So H2 equals E2 divided by eta 2. And so now we get the same value as before, the 460.8. Oh, and we get something different. Yeah, and I think this also looks more correct to me. And
yeah,
then we need to
far field and
yeah, and okay, we need to think about this conversion here once again. Yeah, so that's why we do some check. So this is 1.93 exactly, 3.1 maybe milliampere per meter. Okay, so this obviously does not coincide with this one. And so the problem is with this conversion here that this is, yeah, so I used here, we would need to calculate this intermediate result first, right? So we did the conversion for our original distance of 200 meters. We took this field strength here.
you need H0.
Yeah, so and instead of H1, I should just use H0 here, and then everything should fit. And H0 is something that we have not calculated yet, but that we can do. So this was H1, and H0 is I just use the E0 and divide by also by eta 0, because this is also still in the far field and in the near field. Okay, so H0 is something that we should not have yet, exactly. So H0 is E0 divided by eta 0. And so then we get 2.22 microampere per meter. And now this is what we can take and insert here into this now corrected formula. So let me delete the wrong result here to make some space for the right result. And the right result then should be, let's find the formula where we calculated H2, this one here. And so, yeah,
yes, correct.
Now it should be correct. Unfortunately, I did not spot this mistake earlier. So we get the same thing that we got on the other way. So it's always good to do some checkup. And luckily we did it and we found out, okay, there was some mistake in our previous calculation. And now if we, let's say, convert in the far field, then do the conversion in the near field, we get the same as if we do the distance conversion first and then do the conversion using the field impedance from magnetic field, from electric field in the magnetic field. And so both ways we get the same result of 1.9 something milliampere per meter. Okay, which is, to be honest, which is quite a lot. Okay, so now hopefully we really finished subtask A. Which questions do you have related to subtask A? No questions? No questions in the chat? Okay, so now we can, oh, there's one. Sure, go ahead.
I'm not understanding why you use the for 2 here. E is second formula.
This one here?
No, this one. E, the first,
this one.
Why we use for 2? Not
Why do we have the factor of 2 here? That's a good question. So for the electric field we have a factor of 2, for the magnetic field we have a factor of 3. And these exponents, they come from the theory. So if I open up the lecture slides once again, and luckily they're on the same page. So here it says the near field for the electric dipole, we have r to the power of 3. For the electric field, r to the power of 2 for the magnetic field. And for the magnetic dipole, it's vice versa. And this is what we already discussed for the task before, for this one here. So if you calculate wave impedance is electric field strength divided by magnetic field strength. If we are close to an electric source, to electric dipole, we have more electric field, less magnetic field. And more electric field, less magnetic field means we also get a high impedance field, and we get more electric field if we have the higher exponent for the electric field. Because if you go to some distance that is, let's say, smaller, if you go into the near field, you have something divided by something small is something large, and something large to the power of 3 is getting larger than the same term to the power of 2. And so that's why for the electric field you have this 3 exponent for the higher exponent for the electric field. For the magnetic dipole you have the higher exponent for the magnetic field. Because close to some magnetic source that we have here in this task, we want to have, or there is more magnetic field in the near field than electric field. It's a low impedance field. Okay, more questions?
And
okay.
377 is fixed.
And the 377 is fixed for the far field.
Okay, for near field.
And for near field, it depends. It depends on the distance. It depends on this distance with respect to the transition distance. Yeah, and this is all also more or less nicely written in this lecture slides. So conversion for the electric dipole, both points are in the near field. We use these formulas. Both points are in the far field. We use these formulas. One point is in the near field, one point is in the far field. There is a more complicated formula, but I would just do the transition or the conversion to transition distance first. And so now if we switch to the slide with the magnetic dipole, I think there is one version of the slides where I've marked this in red because as you can see, almost nothing changes, just the word electric and magnetic, and the exponents change the position. 2 changes into 3 and vice versa. Yeah, and that's the thing. And so this field impedance, there is also a source where this is discussed, but here it's not called eta but called gamma, but it's the same quantity. Right? And for the electric dipole we get this high impedance field, for the magnetic dipole we get this low impedance field, and in the far field we always have 377 ohm. Okay. Then let's continue with the next task in subtask B here. How large is the current in the loop? Any ideas for this? The answer is also somewhere given in the lecture slides, and so there is this table. If you remember this table, inside this table there's also the magnetic dipole, and for the magnetic dipole we find some formula here that tells us current, area, P eta that we already use, lambda and r, and that gives us the far field electric field strength. So let me copy this formula here. And so we can now maybe use a second page for the next subtask B and say the electric field in the far field can be calculated according to this formula. So if we want to know the current, we can just convert this formula into the direction of the current, and then we get electric field multiplied with lambda square multiplied with r and divided by all the stuff that's written there, divided by the area of the loop, by p and by eta. So how can we calculate the area of the loop? It said the field is identified as a loop with a radius of 30 centimeters. So we can assume, okay, it's probably a circular loop, right? And so if we have a certain radius, how can we calculate the area of this loop? PR squared, exactly. So well, we could also insert this in there, but now we have to be careful. That's why this radius there is written with the capital R, to not to be confused with this R, because this is our distance. Okay, so we can take our area, insert the area over there, and yeah, so then we need to decide for a certain field strength, and of course what we can use is, this is far field, and this is also far field, what we calculated here. So let's say this is E1 and R1, and then we have far field values, and then everything should fit. So I can just insert the values into MATLAB and calculate stuff there, and then we can think about the unit of this current. So what unit, of course, should we get for the current? Ampere. What unit do we have from the electric field strength? Volt per meter. What unit do we get from lambda? Meter, and we get meter square. From the distance, another meter. From the area, meter square. And from eta, we get ohm. And ohm is volt divided by ampere. And this fits because volt and volt will cancel each other, meter square and meter square and meter meter, and we get ampere, which perfectly makes sense for the current. Okay, so then back to Octave, move the window a little bit and say, okay, at first maybe calculate this area. For this we need to have the radius, it's 0.3 meter, so the area is p times radius squared, some 0.28 square meter. And so then the current is E1 multiplied with lambda squared multiplied with R1, and then divided by the area times P times eta 0. This is how it's called in MATLAB. And so we get a current of 10.7 ampere. Quite a lot of current to create this field. 10.725 ampere. Okay, so we have calculated the current. Would there be some other way to calculate the current?
From near field?
Yeah, we could also try it from the near field. Unfortunately, in this table, there is no formula given for the near field, but we can go back, of course, to the real formulas of the magnetic dipole that were somewhere here. Yeah, so this was, I already skipped. This was the magnetic dipole, this circular loop with this radius. This is the George Francis Fitzgerald guy, I think some Scottish, Irish, something like this physicist. I would need to check. And so here are the full formulas, and these formulas include both near field and far field terms. This is the far field term. These are the near field terms. And so there is one simplified formula that just takes into account the near field terms. And there is one formula that just takes into account the far field terms. And yeah, so for example, we could also try to use this formula here because we have also calculated magnetic field strength in the far field and check what happens if we use this formula. So I will copy this. And so we also have the current there, and we have some other terms. And we would need to think about these other terms. So this is the sine function that depends on the theta angle, on the elevation angle, let's say, in the radiation pattern. What do we do with the sine term? We assume that it's maximum, that it's 1. That we say, okay, this angle goes to 90 degree, and if the angle goes to 90 degree, then the whole sine function will go to 1. The same is what we will do here. E2jkr is just some rotating phasor in the unit circle. If we take the magnitude of this, let's say, then everything will be also 1. And we can also neglect the sign here because we don't take care about the sign. So if we convert this into current, then we need to divide by 2 r squared p to the power of 3, and we need to multiply our h with lambda to the power of 3 with k and r. And so this is also valid for far field, right? Maybe I should add here what we have done here on the top was far field. What we do now is also far field. So we need to have some far field strength, and we need to have some far field distance. And so here we used E1 and R1, so here we can also use H1 and R1. And this should be values that we already have in our Octave window. So if I, if we do this, and maybe we should think about the unit first. So let me move this to here and say, okay, this is also far field. And if we think about the unit first, the unit of the current, what is the unit of H? Of the magnetic field strength? Yeah. Ampere per meter. So then we have another meter to the power of 3 from lambda. What is the unit of K of the wave number? Yeah, it has a unit. And you can check what is the unit of R, what is the unit of the distance? Yeah, meter. And what must then be the unit of the wave number? 1 by meter. So in 1 by meter I will write here. And so then we have another meter squared from there. So we can check, we have meter to the power of 4 and meter to the power of 4. They will cancel, and at the end we will just get ampere, which totally makes sense for the current. So let's go back to Octave and say, okay, the current should be also H1 multiplied with lambda to the power of 3 multiplied with k. I think we don't have k yet, but let's still continue to type this formula. Divided by 2 times the radius squared multiplied with p to the power of 3. Okay, and now we probably get some error message. K is undefined, so k is 2p divided by lambda. And so now it should work, and we get the very same value of 10.725 ampere, which perfectly makes sense. 10.725 ampere. And yeah, it does not really makes sense to start with the next task. So what we can just try out here to see if it works, if we use a formula for the near field, for example this one, which is the main field strength component. So let me copy this formula here and go back to the drawing program. So now we do near field stuff. And once again, we assume that the sine function has which value? Same as here, we say it's 1. And we need to convert this formula back into current. And so we need to have our H field multiplied with lambda to the power of 3 and k to the power of 3 and r to the power of 3. And we need to divide by 2r squared and p to the power of 3. That should be it. So we can check the unit, of course. And the unit should be once again ampere per meter for the magnetic field strength. And then we have meter to the power of 3 here. Then we have 1 over meter to the power of 3 over there. We have another meter to the power of 3 here from this k. And we have another meter squared from the radius. And so all the meters, you can check the exponents, they will all cancel each other. We just get ampere, which perfectly makes sense. And the remaining calculation I can do in Octave. Move my window up a bit. And so now, before I do this, we need to check what was near field stuff that we already calculated. For example, this H2. H2 was in the near field and the corresponding distance was R2, 5 meter. So if I go back to Octave and use this formula with H2 and R2, both values which are in the near field. So I will just retype the formula. I is H2 multiplied with lambda to the power of 3 multiplied with k to the power of 3 multiplied with R2 to the power of 3 and then still divided by 2 times R squared multiplied with p to the power of 3. Maybe I should have not retyped the formula, just copied it. Okay. So hopefully, let's see if we do this, we get the same value for the current, which also perfectly makes sense. So nice check that this really works, because once again, would be quite a strange coincidence if we have done the very same mistake in these 3 different calculations that we have done here. Okay, so we can say now subtask B is also solved. We have calculated this current in the loop, for example, maybe in this power electronic circuit that generates this disturbance with maybe some kind of harmonic of a switching frequency, because a power electronic circuit, but might be a resonant power electronic circuit, usually will not work at 1 megahertz, but maybe in the kilohertz range. But it could be, of course, some kind of switching harmonic that we have there that creates this current inside some loop somewhere on the printed circuit board.